This was what we did on Wednesday. So I still have that 4 or 5 questions listed there, but we went through question number 1 and question number 2. Particularly, we ended at question number 2 on Wednesday when we talk about the casting. And by the way, casting is a very interesting concept, very powerful, but it's also very complicated. So let me just quickly summarize before we move to question number 3 and question number 4. So essentially, we're talking about typecasting is convert a variable or an object of a type, whatever the original type is, to convert it to another type. And I do want to emphasize that casting is a compiler concept. Did I say here? Okay, here is important. I said casting is done by the compiler, not runtime. Okay, well, why did I emphasize this? It's because remember during your first midterm, I talked about the difference between runtime error and compiler time error. And this is more and more become very significant that you need to think about when you develop an object-oriented program, what decision was made or will be made at the compiler time, which decision will be made at runtime. It's very significant here to see the difference is that sometimes the compiler might not have the information until runtime to do the right conversion. And therefore, if you try to do the casting, you thought the compiler should be able to figure out which type to cast. It is not, and which I will show you why. That is really very advanced, but very important topic for the C++ programmer, that you understand under what situation exactly the compiler has no knowledge about how to do the conversion. It's not because the type doesn't match. Even with a single inheritance, you go up, go down, and sometimes compiler doesn't have the information. Okay, I want to clarify this. Usually, the compiler always have the information about how to move up, to typecast to the parent class, but it might not have the knowledge to cast down, to go back to the child class, particularly. Okay. Okay, let me show you one of our students come ask me today office hour. So I want to use this picture to kind of explain what we have done so far about the difference between typecasting using reference, which in our example is GPSDD underscore DD with M sign. That's what we call the typecasting a reference. So when we do typecasting as a reference, so remember, when you have any kind of inheritance, your object, this is a labeled GPS object, but this object has a multiple component. So when you do the casting, essentially you're using exactly the same object in the memory location, but instead you have the what we call reference or pointer. You're pointing maybe sometime at the same location. By the way, maybe sometime it will be a different location. But the thing is that this object, the content of the object has not been changed. It's still essentially before and after the typecasting. These two reference to the object, they basically pointing to exactly the same object, the same content. Okay. But if you do typecasting as a copy, so you can see now the difference between typecasting using reference, you say GPSDD, put an M sign, and then if you do typecasting as a copy, you just do GPS DD. And over here, it's different, is that instead of having this original copy, you create a copy. But when you create this copy, you only create part of the initial label GPS object, because when you want to create or you want to do the copy, you want to get into only the GPS DD portion of the object. And therefore, this is a different memory location, and you lost the label GPS component. Therefore, it's important the system, when you want to convert it back, this is essentially typecasting down to, typecasting up to the parent. But when you typecasting up, the compiler sometimes will allow you to do that if you say you're doing this with reference, but indeed it doesn't have the GPS component there. So essentially the compiler will imagine you might have one, but actually you don't. So therefore this is kind of like an error message we saw. Okay, so that's the important difference I want you to note about the typecasting go up and go down, and also the major difference that why you should always use a reference instead of using copy. Okay, so you know the semantic difference between those two. If you want to do copy, this is fine. You want to make a new copy, but don't cast down. Don't typecast down to one of the derived class, because the compiler might allow you to do that. Compiler might not even generate a warning message, but you know that when you did this, you messed up with some other memory. Okay, so sometimes compiler help us to identify some of the problems, but sometimes the compiler just is not comprehensive enough to basically understand your intention in this case. Okay. All right. Any question? Okay. So let's take a look at the code. So I'm trying to finish a few example with this part. I mentioned this is that cast up via reference. All right, and then cast down via reference if it is a single inheritance. Okay, but you cannot cast down at all if it is a virtual inheritance. Okay, this is a new thing to you. Why is that? I mean, I haven't told you what's the difference between single inheritance and virtual inheritance. It's essentially adding a virtual in front of whatever public and base. I will show you an example immediately. The thing is that why, when you introduce the concept virtual inheritance, even it's a virtual inheritance of single inheritance, in this case, even you cast up with reference, you still cannot cast down, because as I said earlier, the compiler didn't have the information for them to do the right thing, the right conversion, because there's some information only available at runtime. So that is a really important concept in object-oriented programming. Just let you know, you need to know what kind of information compiler can know at the time you compile the program. But compiler's job is just generate the executable. But if they miss certain information that's only available after you start running the program, then the compiler just will tell you error. Let me first tell you what's the error message and what's the difference change. And we will dive into that probably after next midterm to see exactly why is that. But I want to tell you, give you the warning at this moment. So let me do it, make it clean. So my watch says span likely. Okay, don't worry. So give me a second. I will just. Okay, you see that when I do a compiling, everything is good. Okay, I generate all this message. Okay, let me modify just one thing in the label gps.h. Over here, you see that I did the inheritance, but the inheritance is class, label GPS, public GPS DD, right? Okay, now I'm actually, what is a virtual inheritance? The virtual inheritance means that I'm adding a virtual keyword here. I just add a virtual there. And then I do a make again. Let me do a make a clean. Let me do a, oh, okay, it's already coming up. Okay, so you see that when I try to compile the test labeled GPS, and I try to, the compiler try to compile this particular line. What is this line? This line is try to cast from the base back to the derived, right? It's try to cast a GPS back to a labeled GPS using whatever you want. And just look at the message. What it says is arrow. I cannot cast GPS DD to label GPS M via virtual base GPS DD. Why is that? This is called virtual inheritance because my base class is a virtual. Okay, right now I just want to convey to you is that virtual and non-virtual introduce some difference over here that you cannot cast down. You can still cast up. And the main reason is that compiler just don't know how to do it because it doesn't have the information until runtime. So essentially, I'm saying that when you add the keyword virtual, you actually generate or have some dynamics that compiler won't see until the runtime. Okay, we'll explain exactly why this has happened here, but now I just want to tell you this is the limitation, but this is an important limitation for the language to do cast up and cast down. Okay. All right, so let me change it back first. Okay, so now I'm going to go back to this program to tell you a few other things before we move to the next topic. So this is the test program. And this is what we did last time. The first two, this two line essentially is how do you, now I can do this because this is a very simple way of calling a function. You can move up and move down with those two classes. But if you only, so by the way, there are multiple reasons for you to cast up sometime. To call the function in the parent is one of them, but it's not all the purposes. So if you only want to call the function in the parent, in fact, you don't have to cast. You can just directly do this. You see that? What I did is I used the original format of the GPS TLC UC Davis, which is a label GPS object. And then I basically just directly adding the class name. I add the base class name. So, and then so how do you actually specify? It's always the class name with two columns. Then this is how you inform the compiler. I really want to be explicit about that particular function. So in the object-oriented programming language in C++, the function name, you can always add a class name. When you add a class name in front, it will give the compiler enough information to know which version of the function foo you try to call. Okay, so that's all I want to tell you about casting and related to inheritance hierarchy, move up and down. So now the third question I want to talk about, just bring back my notes. So the next topic I want to talk about is, well, how are the object, including the inheritance component, they got allocated in the memory. So we already kind of touched on this. You see that when we did an incorrect cast up and cast down, and we are actually printing the result label is not the teaching learning complex, but instead is printing to West Sacramento IKEA, which means that is accessing the information, because remember I showed you the slide. We kind of don't have the component. When you try to force the compiler to guess, the compiler thinking, oh, your label GPS must be here, over here. And therefore, it's printing that whatever region of memory, but that region of memory is belong to somewhere else, sorry, some other object. So that's why you're printing somebody else's result, which is definitely incorrect in terms of logical error. Okay, so now let's take a look. How do we try to understand where this object is allocated? Because obviously the allocation of the address is an important thing for us to consider. So how do I really figure that out? Let me show you programming. So we're trying to guess where this object is located, but then we have to write program to validate whatever our hypothesis is. So here I start writing a few lines of code. So this part of code is before you go up and down, I try to print a few things. Okay, so some of you might be able to look at the code if you familiar with C program. So can some of you just tell me what this 3 lines of code, not the first line, this 3 lines of code is doing? Can someone tell me what this 3 lines of code is doing? Yes, please. Yeah, so that's good. Thank you very much. Angela, right? Yeah, okay. I gradually learned your name, okay? I sometimes misspell. I'm glad I guessed it right today. So I validate with you. Thank you, Angela. So Angela is correct that this is the address, memory address of the 3 attributes. Because if you think about object label GPS, it's really 3 attributes: latitude, longitude, and a label. And therefore, how do I know where they are? I basically try to print their address. So by the way, this is so powerful. You can know whether this 3 attribute, for example, the first thing you should ask is, are this 3 attribute being put together in a compact format, or is actually they separate somewhere in my memory? What's the case? Because compiler allocate the memory. So remember, when you want to print something, you see that this is an object, is GPS TLC UC Davis dot latitude. That's the variable. And then I just put a parenthesis, cover that, and add n. And if you see something, you have an n sign before that. What's that? That's address. You can call it either address or it's a pointer, C-style pointer, by the way. It's not the C++ reference type of pointer, okay? So now I'm printing all this. So I basically, you can see that in this program, I print a few things. Before I do the first casting, is casting by reference and casting. And then after I do this part of the code I showed on Wednesday, is essentially doing the cast up and cast down using reference. And then I basically print what? I print the few lines here. Is that right? Yeah, I print because when I cast down, I put it into label REF1. And again, I'm actually printing the REF1's label address, longitude and latitude. I did this, okay? So, and then the other thing I did was I did the reference casting up and then copy casting up and then reference cast down. And again, that is another variable called labeled copy1. And then I just print the address of this 3 things. So let's actually take a look at the result. Okay, let's take a look at the result. So this is the original. The original, I said before, you can see that this 3 line is the address, right? This is the 3 line. The first line is address of label. By the way, this is all in hexadecimal. That's the label the address for label, address for longitude, address for latitude. So if you compare those 3, with this 3, which is after up and down via reference, you see that they're the same, right? This 3 and compared to those 3 lines we just look at, they're exactly the same. So that kind of confirms what I draw in the PowerPoint slide. I mean, regardless how you go up and down, it's the same memory location, the same address. So, which means that they really share. That's fine. But if you look at the other one, sorry, I have to move this way. If you compare, sorry, this 3 are basically move up and down with a reference. They're the same. But if you look at this 3, these 3s are basically copy up and reference down. And you can see that this 3 address is different. Here is 2A0, 2A8, 2B0. And here is 1E8, 1F0, 1F8. Okay, there are 2 different copies in different places. Okay, so that kind of verify that, okay, wait a minute, I know where it located and where this should be. So I want to show you a PowerPoint slides about what I kind of copy this address over here. Oh, by the way, I also want to print one thing. Hold on one second. I want to tell you that there is another thing I print. I didn't tell you. There's another thing I print in this figure is I print the object address, the object of GPS, TLC, UC Davis. So this is their attributes address, but I can also take the object like this and then put an M sign. That's the object address. So let's actually look at what the object address it is. So the object address is shown here. You see that? This is the object address. Before typecasting to the base class using the reference object address, so blah, 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 this 3. Okay, so I'm going to put this 4 piece of information in this PowerPoint slide. So let's take a look. Wait a minute, where's my PowerPoint slides here? Okay. Let's take a look at this 4 thing. So this is the object, which is 298. And then the first one is latitude is 2A0. And then longitude is 2A8. And then label is 2B0, right? That's the 4 address we got. Okay, so this is a hexadecimal. So from this, I want you to figure out very quickly about what's the how do I say that? What's the gap or difference between each pair of address? So let's first take a look at that. Is what's the gap of the address between longitude and the label? Hexadecimal, yeah. 8 bytes. It's 8 byte, right? So this gap represents how many bytes of memory we need to represent the longitude. So longitude is what? It's a double. And in the more than 64-bit environment, a double is 64 bits. Therefore, it's 8 byte. So essentially, the gap between A0 and B0 is because starting at A8, A9, A8, and whatever the next 8 byte is exactly the location I'm going to put that double represent the longitude. And the same between latitude and longitude, you see that the difference is also 8. That means from A0, A1, all the way to A7, those 8 byte is for us to store the latitude, all right? And then, of course, starting from B0 to whatever the next, how many bytes, those are being stored to represent the label as well. So you can see that their number one has something I want to introduce you. It's called offset. What is offset? Offset means that what's the address gap between the first byte of a particular variable and the address of the beginning of the object. Okay, so if I ask you, what's the offset of the attribute longitude? Is actually 16. Why? Because the address of the object beginning is 298. And then you skip 8 byte to 280, you can have 8 byte for latitude. And then after this 8 byte, you're actually going to have a longitude. Okay. So that's called offset. You probably don't appreciate why I asked you to calculate the offset. The offset is very important. I will show you later. Okay. All right. Any question in this figure? Yeah.
Why does it say 10 or 16 or 18 or 24?
Oh, I just want to use hexadecimal and decimal. So 18 is a hexadecimal, 24 decimal. Okay. Yeah. Okay. An offset is the address difference between the beginning of the object. You think of object is like this. Okay, the object is the whole thing, right? The beginning of the object is pointing here. Okay, by the way, it looks like I draw the picture. It seems to me when I draw the picture of an object, it always have a GPS DD first and the label GPS. Okay, so just give you to want you to appreciate C++. Depending on the situation, that order will switch. That's why sometimes we need to study offset, because in some cases, the GPS DD first, but sometimes it's a label GPS DD go first. I will explain to you. Don't worry, don't panic. You will learn those. It's just some knowledge is so important that the C++ programmer can tell Java and the Python program, hey, you never need to worry about this kind of detail. Okay, that's the only thing that's bragging. Okay, that's a bragging piece of knowledge you can learn. All right, so does that answer your question? Okay, I hope. All right, so any other question? Yeah. Can you repeat your question again?
So the object at the end of the largely just to this, could you explain why it's different?
Why? What's your name? Tiffany? Why? How can you ask me a question like this? It's totally understandable. I'm not offended. Okay, I'm waiting for that question, by the way, for about 20 minutes already. Thank you. Tiffany, is that right? Okay, thank you. So it's a very good observation that why I have my object address, because if you look at the picture here, it seems to me I'm pointing to the first byte, the GPS DD, right? But there's a gap. There's a gap that's actually show up here is 8 byte. You see that? Why I have this 8 byte? I said latitude started with 08. And why do I have this 0? What is that 8 byte? That is exactly why we need to talk about virtual function. In virtual function, we need to put a pointer that pointing to something called vtable. So let me tell you that, remember I said the compiler doesn't know how to do the conversion. Why is that? Because this pointer is giving the information about how to access some other element in the object. And that pointer will not be configured or set until the runtime. That's why whenever you have this vtable in certain way, the compiler will not be able to move up and move down. So, okay, good. So you remember this 298A0. Let me actually just change one thing to the code. Okay, so the source of the question in this case is because in GPS.h, if you look at the code, I have a one function that's actually virtual. Because whenever you have virtual function or virtual base, one of these two cases, I need to have that 8 byte reserved for vtable pointer. Vtable is something which is related to what we call function pointer. It's stored together with the class, and where each of the object has a pointer to that. Okay, so I'm going to cast this out. Not cast, comment that out, okay? Please remind me to take it back when we're done with this class. Label GPS.h. I also have a virtual here. Is that right? Yeah, I have a virtual here. Let me get rid of this too. Okay. Well, maybe this won't compile. Let me see if it will compile. Yeah, it won't compile. So I have to do this. The reason I have to do this is just because to do this demo. I still need to have this. I know what I want to do. But I want to get rid of the virtual. So now this two function, they're both regular function. And then I have to change this one the same way. So essentially, I convert that to a non-virtual function. The dump to JSON. Okay, let's clean and make. I hope this time I can get it compiled. Okay, perfect. So now let's run the program. I run the program again. And let's look at this for address. Let me copy this. And go back to my PowerPoint. I want to get rid of this. It's confusing. It's confusing. So let me show you where's the object. The object address is here. Let me highlight it with whatever color I can have. Sorry about that. Highlight to be red. And now this is the 3 lines we had earlier. Bring it up. If you just look at this 4 line, now you see that gap disappear. I no longer have the gap. The first byte of the object is 88. And the first byte of the latitude is 88 as well. Okay, that's the difference, is because we have something called virtual function, right? It's a virtual function because we have that. And now that after I remove virtual function, voila, that particular gap that Devine pointed out is gone. Okay, so you can see that it's tricky whenever you add a virtual, something is going to be different. Okay. All right. Any question? All right. So now I'm going to move to number 4, virtual function. Okay. So I have a base class and derived class. I'm trying to first explain the concept using PowerPoint slide, and then we can look at code as well. Okay, so you see that what I did in my earlier twist about my code, I essentially has the same function. I mean, I call it dump to JSON. I remove from virtual to non-virtual, but now I'm just using the foo as an example. I use foo as an example. So you can see that I could have 2 ways to define this function foo. I can just use that as a regular function, or I can use the keyword virtual. But besides, I introduce an 8-byte gap between, at the beginning of this object, semantically, what does virtual function give us differently than non-virtual function? That's what we try to understand, okay? So let me just set up on this particular, the slides is that I have a function in the foo. I actually have a 2 option on the base class, exactly the same thing. I have a derived class, okay? So let's take a look at the first example. If I chose to use non-virtual function. I choose to use non-virtual function just like this, define. And what happened? Okay, here. Okay, now I'm writing a code looks like this. Okay, I hope you'll understand the notation. I'm using directly the class is my base or my derive. Okay, so I create a object called my base, object one, and then I create another object called my derive object two. So my derive object two is here, my base is here. Okay, so then I call object one dot foo, object two dot foo, and then I call casting my base and object two dot foo. Okay, I have this three line. So can you tell me which of these two functions you think the code will call? How about the first line? If I call object foo is up, I shouldn't say up, it's base or derive. Object one is base, right? How about object two? Object two is going to be what? Derive, right? How about the third one? The third one, if I casting object two, it should be what? Base, right? It still be base. Okay, good. You guys are getting it right. So this is the way it works. Okay, the one and the third will go to the base, and the second will go to the derive. If this is a non-virtual function. Okay, now let's do the same thing with virtual. Now is the same, exactly the same piece of program, except I add this virtual keyword. So let's take a look. What is the first line? Base or derive? Base. Okay, that's correct. How about object two? Base or derive? Derive. Okay, that's correct. Number three. What's the base and the derive? I mean, you can probably say virtual function is going to introduce difference. So this one, even I do the casting, is going to be the derive. Okay, the difference. If you think about that third one, only look at the third one. The first two is just camouflage. Okay, doesn't matter. But the third one, as I show you, when you do casting, you're actually going to call the base because you change the type, you convert the type, even though it's a reference. But if you're doing virtual function, so this one, even you cast to something else, it will still execute the derived version of foo. That's the key difference between virtual and the non-virtual function. Okay, now I want you to guess. Why is that? What mechanism or what is the feature for the runtime to decide that this one need to call this one? What should, I mean, how do you describe it? I show you two different programs. I show you this language feature that's going to obviously going to behave somewhat differently. But how do you explain in your words about what's going on here? Why virtual function is behave like this? I mean, this question, by the way, is vague. It's very, sometimes I just want to ask your opinion. And guess is, we don't want to worry about the guess is correct or not, because we always write the program to validate. Any guess about what's going on here? Yes, please.
I think I may be misunderstanding the question, so let me know if it's wrong, but if I'm understanding correctly, if you use virtual, it does that at runtime. So that's why it doesn't call the object as if we're doing it by the virtual keyboard.
Okay, I try to parse your language, but I think you're hitting it. It's just anybody else want to describe another way or similar? So let me ask a different question. Do you think casting, in this case, do you think that casting has any impact on the calling of a virtual function? Does casting change anything? I mean, obviously, non-virtual function, the casting is going to change. Yeah. Yes. Okay.
I feel like it's going to be slower.
It has, well, it will be slow, but the slower is not because of the casting itself. Because remember, casting is done by what? Is runtime or compiler time? Compiler time. So casting shouldn't impact the runtime performance. It may be compiler time is slower, but the runtime is not, right? You want to say something?
Is it going to go, so you passed it to object one, or you passed it to the base class, but then instead of going directly to the base class, since it's a virtual function, does it go to the table, and then it's like, oh, this is object two at runtime, and so then it picks, instead of—
That's correct.
Fix it runtime instead of compile.
That's correct. That's exactly right. So what virtual function is doing is that it's not directly linked to the code. Why is that? Because the compiler time, you actually don't know the true type of that particular object. You don't know. So therefore, how do I find the right function? You store the pointer to the function in the vtable structure. But by the way, that vtable structure is not directly with the object. It's associated with a class. And your vtable pointer will pointing to that table. That's why we call vtable pointer. It's basically a table per class. And therefore, when you call a function, the compiler generated code is essentially to retrieve the value you store in the vtable and then call that function pointer. If you're the first time you heard about this concept, I know it's super confusing, but gradually you understand. There's something called vtable somewhere associated with the class derived or labeled GPS. And in the vtable, it stores a bunch of things, but one of the things they store is each of the function pointer to all the virtual functions. So it's only virtual function. If this is not virtual function, it has no position in the vtable. It's only you have a virtual function you will go to. So essentially, vtable store two things. One is for vbase, one is for virtual function pointer. And therefore, think about what happens is that when you try to call the function through, the compiler knows. The only compiler only know it's a virtual function. Is not a regular function. So the compiler doesn't know which is the correct version because the compiler doesn't know the true type of this particular object at any time. So by the way, I should introduce another concept. What do I mean by true type of an object? So I want to say this. There is an important concept is that, let me just type it up here. There are two particular timing we need to worry about. First is what we call object creation time. Means that this particular object at this particular moment of time, it got created. And the other timing is what we call object member function calling time. Okay, so there are two important timing. One of the timing is when the object was created. The other timing matter in this is that at the time I'm going to call that particular member function, maybe it's a virtual function, okay? So the thing is that why object creation time is important is that where is the object 2's creation time? Where in this picture, in this code, is object 2's creation time? I'm talking about in terms of the line of the code. Is actually the second line in the code. This is creation time for object 2. Okay, that's the creation time. Because when you got created in this time, you can start an object called object2. So at that time, you clearly know what was the type, what was the class, what was the object type that this object2 was created. So this object is might-arrive when they created. So essentially at that time, the vtable value was set at that moment. But this is runtime, not compiler time. So by the way, the compiler, I mean, this is a little bit tricky, but I want to say this, is that, I mean, you can say, well, compiler, why don't you do this? You actually look at this piece of code here. Sorry, go back. You look at this piece of code over here, and you say, hey, this is the place I create the object. And then later, when I ask you this one, oh, I should know because I have the code over there. Okay, in the small program, the compiler might be able to figure out. But in general, it's not the case. Essentially, that particular object could be created by some other function. It might be created in some way that it doesn't even have appropriate syntax, it only have an address being passed in as an integer. And therefore, in general, you really don't know that what is the type. So essentially, the line number 2 and this 2 line, it cannot be correlated by compiler in general. So essentially, object creation time can only be determined at runtime, while object calling time is actually can be determined by compiler time, because the compiler can know, okay, here's the time you really call the function. But the thing is that to decide virtual function versus which version of virtual function, you really need to know what is the type when it was created. So let me repeat the last sentence and it will say happy weekend to you. So what's the virtual function? The virtual function is actually determined what is the object, what is the class or object type at the time it was created. Based on that information, you can determine which version of function you should call. And that information won't be available until runtime. That's why the compiler can't do anything. You have to do whatever. So this kind of casting doesn't matter. Okay. All right. So you all have a good weekend. And if you have any questions, let me know.